former class, we studied in this. We find opening the box, the structure of the computer is different in several companies, in several computers. We find the capacitive multi-touch LCD screen is in the former. This is an iPad from Apple company. This is computer board in the Apple iPad. We find the computer board is an important component in several computers. Inside the processor, we find the CPU. In CPU, the data bus. His role is to perform operations on data. He can control sequence, data path, memory. The cache is important memory. We find the cache is small and fast. He is a SRM, we call thread memory. Thread memory is a very fast memory, but the thread memory is the size of SRAM.
Size is small.
But the SRAM memory is fast. He is fast. He is very important. So we use SRAM to
Cache memory.
Yeah. The cache memory is the middle from CPU and the main memory. So we find immediate access to data is his role. Immediate is immediately we find his role or his name is in the middle. This is the Apple A5 CPU. We find processor, and processor. So we can see the A5 can have 4 processors. It is multiple processor. We find the processor, in the processor we find ARM, we call ARM core. ARM core is useful for the processor. We can't divide the CPU. The CPU is very we call, in Chinese we call 集成 紧凑 Are you here? 紧凑 The CPU is not, or we can't divide, we can't cut. We see the CPU as a part. As a whole. As a whole. Yeah. The abstraction helps us to deal with complexity. The complexity is the characteristic or the feature from all our computer. We find the abstraction can hide low-level detail. He can hide low-level detail. It is useful for computer users and computer programs. Instruction set architecture, ISA, is very important. We find the instruction set in the CPU, but we can't use, we can't touch. The instruction set is useful for CPU, not for user. For user, we can't care. We can't see the instruction set in hardware or software. We use programming language to design the software. We can't use instruction sets to design software. Application binary interface is very important for users. The ISA plus system software interface is for the software. Implementation, we find the details, the underlying and the interface is very useful. We can find in the PPT, we find volatile main memory, no volatile second memory. This is an
non-volatile.
hard disk.
Non-volatile secondary memory.
This is not main memory. This is an secondary memory.
Yeah.
So secondary memory, the size of secondary memory is very big.
Big. Yeah.
But the speed of the secondary memory is very slow.
Yeah.
We can find the cache is better or is faster than the secondary memory or main memory. This is a driver.
CD drive.
This is not useful in this or in the future. The disk is not useful for the computer and the laptop. We can't find the driver in the laptop. So you can find this is a flash memory. In the U driver, for example, in this U driver, we find the flash memory in this driver. So you can find every SD disk is useful for optical disk and other computer and other video computer. So you can find the DVD and the CD-ROM is the term for the driver. So you can find the logo DVD. Okay, optical disk is the name for this. So we can find the network. This section, or we can find the router. The router is very useful for our computer and for our school. We can find every router in the school, in the home. We find the router can promote or provide the Wi-Fi service. So you can find the communication, resource sharing, no local access is the networks. It's the use of networks. We find LAN when we call Ethernet, we call Internet, and the Wi-Fi and the Bluetooth. This is the network link.
RJ45.
This is RJ45. Okay, the technology trend is shown in the picture or in the image. We can find in 1951 we find the Vulcan tube. His cost is 1. So we can find relative performance divide cost. His number is 1. You can find in 2013 we can find ultra large scale IC. Ultra large scale IC is in Chinese is 集成电路. In English is ultra large scale IC. IC is from VLSI. This is a simple word or simple term. We find the number is big and big. The number is big is useful. We can find the price is lower than before. So you can find the electronics technology continues to evolve. We find the increased capacity. We can find the increased capacity and the performance is very important. Reduced cost is important than others. So we can find we use reduced cost to use or to product the useful computer. Semiconductor technology, we can find that silicon is the term in semiconductor. In silicon, we find as materials to transform properties. We find conductors, insulators, switch in the three components. Manufacturing ICs. The flow of the manufacturing ICs is from this section to this section. So you can find a flow chart or flow in the picture. We find the proportion of working die per wafer. So you can find the silicon in and the shape to customers out. So the manufacture IC is very important and very useful in our computer or in our CPU. So you can find the Intel Core i7. Intel Core i7, this picture is can show the details in CPU. You can find the 300 mm wafer, 280 chips, 32 nm technology. Each chip is the size of this. This is Yes. So you can find integrating the circuit cost is very lower and lower than before. The number of the cost must be small or lower. Non-linear relation to area and the defect rate, we can find the defect rate is lower than before. So these are useful for our computer, for the manufacture of our computer. Okay, define performance, we can find the four image. The four image give us a question: which airplane has the best performance? We find 1, 2, 3, 4. The blue section can show the different size or different number. So you can find Boeing 777, Boeing 747, and other. We can find the airplane. You can find the passenger capacity is different. We can find the difference is from the four picture. So you can find the picture. This is relative similar. So in this and this, you can find some are bigger than before, and theirs and others. So, okay, response time and throughput is very useful. Response time is how long it takes to do a task. Throughput is the total work done per unit time. How are response time and throughput affected by two important roles? One is replacing the processor with a faster version. Two is adding more processors. We find the two is useful, but the price of two useful advice is different. Adding more processors must need more price. We'll focus on response time for now. Okay. The elapsed clock time and the CPU time, we can find the CPU time is important. Time spent processing a given job, he can find the discounts I/O time. I/O is show input and output. Other jobs shares, we can find the time spent processing is very important. So you can find compresses user CPU time and CPU and the system CPU time. Different programs are affected differently by CPU and the CPU performance. So we can find the CPU is important for computer, for performance, for system. So we buy the computer, we compare several CPU to choose. CPU clocking is the operation of digital hardware governed by a constant rate clock. We can find 1 clock, 2 clock, 3 clock. The image, the future is shown clock period. The clock we call cycles. We can find in the clock period, we find 1 and 0 is negative and
positive.
It's
positive.
Positive and
negative.
Yeah. From the data transfer and the computation, we can find in the flow of data transfer, we find the data flow. So we can find the update state is small, or the time or the period of update state is very small. The clock period, we can see the duration of a clock style. For example, 250 PS is shown per second. We can find 0.25 ns. So the clock frequency, we can find the cycle per second. We can find the frequency from CPU or in CPU. In the CPU, we find the 4 GHz is the high frequency.
4 gigahertz.
4 GHz is very big. We can find the high frequency and the high capacity, but the high frequency and the high
It's very higher.
Yeah, very high. The high frequency is not useful or is not good for the computer. In the computer, we can find the hertz, the frequency is popular 3 or 2.8.
2.8,
yeah,
2.5 like that.
From 2 to 4
Yeah.
in this scale.
Gigahertz.
Very popular. Yeah. Here is the upper, here is the lower.
Yeah.
So the CPU time is computer that can compute by this equation. CPU time equals CPU clock cycles. Then clock cycle time. We can find CPU clock cycles divide clock rate. The performance improved can by three methods. One is reducing number of clock cycles. Reducing number of clock cycles can effectively reduce. The 2 is increasing clock rate. 3 is hardware designer must often trade off clock rate against the cycle count. So you can find the performance improved is useful. can find this is an example. You can find the clock rate equal this. The clock cycle equal this, and the clock rate is this number. So we can find the demo is computer A has 2 GHz clock, 10 second CPU time. Designer computer B, we can find the aim of the computer B is for 6 second CPU time. The 6 second is lower than 10 seconds. We can do faster clock, but cost 1.2 clock cycles. The former is 1.0 clock. So the clock cycles improve. Okay, instruction count and the CPI. You can find the CPI is very popular and very important. Clock cycles equal instruction count cycles per instruction. CPU time is instruction count, CPI, clock cycle time, and you can find the equal instruction count, CPI divide clock rate. Instruction count for a program you can find, you can determine by program, ISA and compile. ISA is the instruction set architecture. So the average cycles per instruction is very useful and very important. The average cycles per instruction is CPI. CPI can be determined by CPU hardware. Each different instruction has different CPI. Average CPI is affected by instruction mix. So the CPI, the number of CPI, we can find the big of CPI, the useful of CPI. Okay, here is the example of CPI we can see. This is the CPI example in the PPT. So we can find the performance summary. We can find the performance depends on the four sections. One is algorithm. 2 is programming language. 3 is compile. The 4 is instruction set architecture. You can find algorithm affects IC. Possible CPI. Program language affects IC and CPI. Compile is affect IC and CPI. The instruction set architecture affects IC, CPI, and the time. Okay, the power trends. The power is very important and useful. We hope the power is lower and lower. We can't see. We hope the power is lower than before. So you can find the trend is from this. The top is the trend. Okay, we can find the decrease. Yeah. The decrease is the CPU is multiple. We find the former CPU is single core. In this point, we find the decrease because the CPU divide 2 or 4 or 8 cores. In the CPU, we find the cores of the number is binary. 2, 4, 8. Yeah. So because the divide of the CPU, the power is decreased. So you can find in CMOS IC technology, power equal capacity, load, voltage, and frequency. Voltage is very important number. The voltage, the number of voltage, we don't hope the high voltage. The high voltage, the high power. So we can find the voltage, the scale of voltage. You can find the 5 voltage to 1 voltage. you can find the number.
Maximum and minimum.
Yeah, is decreased. Okay, you can find we want reducing power. So we want reducing power. We suppose a new CPU has 85% of capacitive load of old CPU, 50% voltage and 50 frequency reduction. So the power wall, we can't reduce the voltage further. We can't remove more heat. But the new CPU, the new power can reduce because the 50% voltage and 50% frequency reduction. Uniprocessor performance, we can find the trend. The trend we can find is from 1978 to 2015. We can find the trend is very increased. We can find the increase in CPU frequency and the power, the instruction level, parameters, and memory latency. So you can find the number of this is the performance.
Last one is Intel Xeon 4.
What?
The problem.
This?
Xeon, yeah.
This is shown in Intel Xeon 4 cores. In this, we find the higher frequency and the power CPU.
3.6 gigahertz.
Yeah. The number is 3, 4, 9, 6, 7. Yeah.
But now AMD Razor our brand AMD Razor in 2018.
But shala to ite korane gel.
The year 2014.
No, the figure is shown as the number. The number is from this. Yeah. This point is shown in this section, this position, because the line is 10,000, is 100,000, and then 100,000. So this is 10,000. So the number is in this is correct. Okay, multiprocessor is the current processor. Microprocessor is very important in our current computer. More than one processor per chip is the useful method. In the before or in the former CPU, the processor has one core. But in the current CPU, we can find the processor has 2 or 4 cores. So more than one processor per chip. Chip is one chip. We can find it requires explicitly parallel program. Compared with instruction level parallelism, we can find hardware executes multiple instructions at once hidden from the programmer. We can find the programming for performance, load balancing, and optimizing computation and synchronization is the important works. This works is hard to do. You can find load balancing is very hard for the computer. You can't balancing every component We can find the components in our laptop or computers. We can find some components running power. We can find some components running lower. So the balancing is a very interesting topic in the operating system. So in the OS operating system, the teacher will continue or will talk the balance. Okay, the benchmark is the data set. We can find programs used to measure performance and the standard performance evolution curve. You can find the CPU 2006 is the symbol of the benchmark. SPEC is the benchmark symbol. We can find the summarized as geometric mean of performance radius in 1 and 1. The CINT 2006 is for interval. CSP 2006 is for floating point. Okay, this is the number or the results of Intel Core i7 920 or 920. You can find the number of the different description. We can find the name has different names. We can find the instruction count, the size of instruction count. The bigger is this, the small is this. But in the CPI, we can find the size or the number of CPI is lower, can show the power. The clock cycle time is small, but the clock cycle time is same for the CPU, for the several CPU. We can find the clock cycle time is same from this i7 CPU. Execute time is different. The execute time is small, is very useful. The performance, the reference time is small for useful. So we can find the review T is computed by the execute time and the reference time. Okay, we can find this PPT. We can find look back at IT power benchmark. At 1% of 100% load, we find the power is 258 watt. Yes, in 60% load, we find the power of CPU is 170. 170 is show or can show 66% from 100%. At 10% load, we can find the power reached 121 watt. So you can find at 10% load, we must use 47% power. So we can find at 100% load, the IT power can useful and can describe the capacity of the computer. Google Data Center operates at 1% to 50%. At 100%, this is shown we find less than 1% of the time. Consider designing programs to make power partially to load. So low power at idle is the fallacy. Okay, myths. MIPS can show millions of instructions per second. We can find the millions of instructions per second, can number or can compute the capacity of CPU. MIPS equal instruction count divide execute time. We can find the CPI and the MIPS can show the capacity of CPU. Okay, this is the last PPT from the chapter 1 PPT. We can find the cost performance can improve or is improving. Due to underlying technology development, we can find the cost performance is improving. Improvement is very useful. Hierarchy layers of abstraction is the important architecture in both hardware and software. Hierarchy is the important architecture or the important characteristic. Instruction set architecture we can't change. We can use or we can't use because the instruction set architecture is in the CPU. We can't change, we can't touch. The hardware and software interface is for programming. Actual time is the best performance measure. So you can find in several computing number, you can find time is very useful. Power is a limiting factor, but the power, we compute the power in several conditions, not in most conditions. We can find the power used parallelized to improve the performance. Let's have a rest. 10 minutes. Lecture 4 PDF. We can find he is shown memory management and usage. In the lecture 5, he is shown floating point. In lecture 6, we can find is the instruction to machine language. He is the symbol of RISC-V. Yeah, the RISC-V is very, very important and very important symbol in machine language. But we can't see or we can't understand the machine language. You can find the lecture 4 and lecture 5. We have given the materials for the students for yours. You can see in detail. We continue lecture 6, the great idea in computer architecture. Okay, we can find the important content is instruction in induction to machine language. So you can find this image can show the machine language. The machine language can accumulate one in this block. We can find in the page from machine language, you find a symbol is Fortran. The Fortran is a very early programming language. You can find in the image, we can find every point and every hole. The black section is shown hole. Yeah, is a hole. So let's see. The review the last lecture is the C memory layout. You can find the static data code heap is the 4 layout. You can find in the image the code, static data, heap or stack can show in the structure. Okay, we can find in the great idea 1 the levels of representation or interpretation. We can find we are now here. We are not now here. In this section is C program. In this section is list file. So in the organization computer, in this class, we can find we lower the understand level. We hope to understand this assemble language. Assemble language is very difficult.
Yeah.
But assemble language isn't useful for current programming. We can find in several programming language, in several circumstances, we can't find assemble language. So, in a world, we find assemble language is not important. The C program language is very important. So you can find we understand 1, understand 2, we don't understand many machine language.
Machine language.
The machine language is 0 to 1.
Binary.
Yeah. The flow of 0 and flow of 1. Okay, we can find assembly. We talk assembly language is not useful or not, it isn't important, but we must understand or see the assemble is what. Assemble, also known as assembly language, we can find the symbol is ASM. Assemble language is a low-level programming language. A low level is compared for C. The C is a
high-level language.
Yeah. The low-level programming language where the program instructions match a particular architecture operations splits a program into many small instructions that each do one single part of the process. You can find in the C program we can use one equation show or describe the operation. But in the assemble program we find the three lines can show the left of one equation. So in C program we can find the code is simple or is useful. In the assembly language you can find add, sub. So we must use 3 lines assembly program can show one equation in C program. You can find B, C, D, E is 4 variables. You can find S1, S2, S3, S4.
There are 5 variables.
Yeah, can show the 4 variables. But you find T1 and T2 is temporary variable. In the assembly language, we must use temporary variable to show the immediate result. So the assembly language, the assembly program, most programmers can't touch and can't understand.
Because it's work with register.
Yeah. Compare older programmer. Older programmer can like assembly program.
Yeah.
In 40 years or in 30 years, we find the current programmer can't use assembly language. But we must understand. We must show, but we don't use. There are many assembly languages. This is 3 points. A low-level programming language where the program match the particular CPU, particular architecture. Each architecture will have a different set. This set is instruction set.
Yes.
Yeah. This set can show instruction set. You can find in the former we find the instruction set. The instruction set we can't touch, we can't change, but it is important.
Yeah.
He is the basic of operation. He is the basic of CPU. Okay, assembly is not portable to other architecture like C.
Yeah.
C can portable. Assembly is not portable. So you can find the different company. One company is Intel. So you can find the mainstream instruction set architecture. One famous company is Intel. The architecture symbol is x86. So you can find x86 is famous for the world or for the whole computer world. You can find Intel and AMD is two companies. The companies produce 16-bit, 32-bit, and 64-bit. Different size or different CPUs. From 1978, 1985, and 2003, we find 1, 2, 3 from the big and big. So in the future, the 64-bit can improve 128-bit.
Yeah.
So you can find the design is CISC and the RISC is different. RISC is you can find in the ARM. We talk after. We can find the register memory is for Intel for the top x86. You can find the little index. You can find the MacBook and the PC in the current. We find the x86 instruction set is for i3, i5, and i7.
8086.
This symbol is current computer in the market. Okay, let's see the ARM. ARM is the different famous company. The ARM product, ARM architecture. The architecture we can find the designer is ARM. ARM is the the name of company. We can find the bits. He is 32 and 64. So you can find in 1985, the 31 years ago, he introduced the ARM. So the ARM design by RISC. We can find this chapter is from RISC. So you can see the index is little as before. This is little as before. The smartphone smartphone or cell phone, we can find the iPhone, Android. So you can find this is embedded systems. So in the embedded system or embedded computers, we can find the ARM architecture is famous. So the ARM instruction set is different from x86 instruction set. So you can find the third company is RISC-V. The RISC-V you can find the RISC-V is designed by RISC. You can find in 2010 or 2010 the University of California, Berkeley. This is a famous university in America, in USA. The University of California has several schools. So Berkeley is famous because his computer science, the level of computer science is very high. So we can find the University of California in the USA is very famous, or in the whole world. So we find the risk is from risk 5. The load store of the type is from risk, and the encoding is variable. You can find in this risk 5 instruction set is suitable for our ebook. So the 3 famous companies is currently very famous. So you can find one word, mainstream. Mainstream is show it is famous. Which instructions should end assembly include? We can find there are some obviously useful instructions. We can find add, subtract, and bit shift. Read and write memory is very useful operation. But what about only drop the next instruction if these 2 values are equal? 2 is perform 4 pairwise multiplication simultaneously. Add 2 ASIC numbers together. We find in example these 3 points are different or are difficult. Okay, we find the complex and the reduced can show CISC and the risk. Risk, the first word is reduced. CISC, the first word is complex. Complex and reduced is different. We find in the early trend, we add more and more instructions to the instruction set. In the early, we find the more and more instruction can do more and more works. But the more and more instructions reduce complex. Yeah, you can find the size of instruction set is bigger and bigger. So the complex is the result. So you find, all the scientists find the complex is not useful or isn't good. So we can find reduce is the method, or we can cut. Reduce is then can show decrease. We find cut the size of the instruction set. Only the size of instruction set decrease. The useful or the instruction set can useful. We find in the system, we find 3 point is very difficult. 1 is difficult to learn and comprehend the language. 2 is less work for the compiler. 3 is complicated hardware runs more slowly. The slowly is very important for the user. The user can't see, or we don't hope the slower. We hope faster and faster. Yeah. Opposite philosophy later began to dominate. We find the reduced instruction set computing. So you can find in the ebook risk as the logo in the book. So we find the risk is the effective or useful method in the instruction set. Simpler and smaller instruction set can make it easier to build faster hardware. So you can find easier and faster is positive. Yeah, we can find easier and faster in positive. So we find that software do the complicated operations by composing simpler ones. So the simple is good. The complex is is bad or isn't good. So you can find the risk is the symbol from our book in our PPT. The risk is very important. Risk dominates modern computing. So you can find in this question, how important is this idea? We find the risk architectures dominate computing. ARM. So you can find in the former PPT, ARM is risk, and all smartphones use ARM. ARM is for most smartphones.
Yeah.
In Apple company, in Apple cell phone, he used the CPU from Apple company, A5, A6, A7, A8. Yeah. In current cell phone from Apple company, we found the CPU size. The CPU symbol is A11, A5. So you can find ARM and Apple is different company and different products. So you can find the old Cisco architectures include x86 ARM RISC-like, but the x86 ARM-like RISC is not RISC. So the new or current architectures, we find RISC architectures. In 2017, Turing Award to Paxson and Henderson. The Paxson and Henderson is the author in the book. So the book is very famous. You can find in the website or in the Google, you can find the Paxson and Henderson. Is the two famous scientists. Okay, RISC-V is what we'll use in class. We find the 5th generation of RISC. So you can find RISC-V. 5 is 6th generation. So you can find RISC-V, the 5th generation of RISC designed by UC Berkeley. It is shown in the former PPT. You can find one professor, Christie, Asadik, and the Adapter Lab. This is the famous professor. Open source instruction set specification is useful for the whole world. The laboratory or the lab can experience rapid update in industry and academy. So we find the scientist from USA, from America, he can touch and he can use the technology to in the industry and academy. He is very famous in industry and he is very famous in academy. This is important. In China, these scientists can't touch or can't do industry and academy. He simply do industry or he simply in academy. He can't both. He can't touch both. The two fields is different in China. In USA, in America, we can't find the method or we can't find capacity we are studying. Okay, appropriate for all levels of computing, we find inventing the microcontrollers to supercomputers. Yeah, you can find 1028 bit is the size of the values. Designed with the techniques used in mind, we can find the RISC-V is very useful. So you can find the RISC-V resources we give or the lag 6 gives the URL, useful resource link URL. You can download from the URL, you can find the full RISC-V architecture. But the architecture show the book of the PDF file of the architecture is very big. You can see and you can look, but you don't look in details. Everything we need for CS61C is in for our class. So you can find in this URL, in this PDF file, you can find the GUI code. Okay, we find the RISC file. We need see the registers, assembler code, blah blah. We can see registers. You can find registers is very useful in CPU. Hardware use registers for variables. So you must know the registers is in CPU. Unlike C, assembler language doesn't have variables, as you know. Instead, assembler use registers to store values. So the register is memory, is a small memory. Registers are small memories of a fixed size. He can be read or be written. He limited in number and he is very fast and low power to access. So you can find the VLSI can show the registers. So the registers is in CPU. We can't touch, but we can use. Okay, we can find the question is registers vs memory. You can find what is more variables than registers. Keep most frequently used in registers and move the rest to memory. We call it splitting the to memory. Why are not all variables in memory? Smaller is faster. Registers 100. 500 times faster. So you can find the register is very faster, but is smaller. If the register is faster and bigger, it is very useful for the future computer. So we can find every or several scientists must or can introduce or can product the bigger and faster registers. If the bigger and faster registers can be productive, we can hope we can find the memory can give us the more capacities. Memory hierarchy is very important. We find the hierarchy is the multi-level. Yeah. Registers have 32 registers. You can find the RAM has GB level, SSD has GB level. In the thing, 1000 GB is equal 1 TB. So you can find the register, RAM and SSD is hierarchy, is multi-level. Yeah. So if the register can touch the size of the current SSD, we can find the useful in register. In the future, SSD, the size of SSD can touch the bigger. Yeah, so register can touch GB or TB. The size or the capacity of register is more useful. Okay, we found the great idea 3. The great idea 3 we need to study principle of locality and the memory hierarchy. Please remember the principle of locality. Locality is very important. Locality in Chinese is 本地化 locally.
Okay.
局部 locally 局部. So you can find the memory hierarchy is the figure. You can find from the top to the bottom. You can find the big of the bottom, the small of the top. In the top you can find the CPU. In the bottom you can find the file memory.
Virtual memory.
Yeah, you can find the virtual memory in the operating system. And solid state memory.
SSD.
Yeah, is SSD. Physical memory is main memory.
Is RAM.
CPU cache, processor register. So you can find the register is very small.
Yeah.
His level is very high. So his size is very small.
Yeah.
It is suitable. So you can find the CPU, the level of CPU is the top. You can find the physical memory is the memory. The memory is main memory. So you can find the principle of locality, the super fast, average speed, slow. So you can find in the secondary memory, the slow is suitable. So the price of secondary memory is lower. Yeah. If the secondary memory, the speed of secondary memory is faster, we hope, or this is the hope of users. We can find how many registers. The trade-off between speed and availability. We find that more registers can house more variables. We find RISC-V has 32 registers.
Yeah.
Important. In this, we find 32 is the number of registers. X0 to X31. Each register is 32 bits. So you can find 32 and 32. You can find the size and 32. Multiple 32. The size. So you can find the RISC-V is the section. Okay, RISC-V registers, we find X0 to X31. We find the 32 registers can hold the program variables. We find the register name and the register ID. The number of the
register number.
Yeah, X number. We find the ID. Register has no type. In the C, we find the type of variable is important. But in the assembler language, he has no type. He is number.
Yeah.
He only number. The special register is, we find the 0 register. The 0 is very interesting. In every class, we find the 0 is the interesting topic for the class. We find the 0 appears so often in code and it is so useful that it has its own register. So we find the X0 or 0 always has the value 0 and cannot be changed. It can't be changed. If the 0 change, we find the problem can produce. So you can find any instruction writing to X0 has no effect. So X0 is a very interesting register. Okay, we give a summary of the registers. In high-level language, number of variables limited only by available memory. ISA, instruction set architecture, has a fixed small number of operands called registers. So you must remember register. Special locations built directly into hardware, and we find the benefit of register is it is extremely fast. The drawback of register is operation can only be performed on these predetermined number of registers. So we find every interesting topic has benefit and drawback. So in China, we talk every topic from benefit and drawback. We can't talk only benefit, only drawback. We talk benefit and drawback in China or in Chinese. Yeah. Okay. The class is in this. So in 10:15 we
Yeah.
continue.
Thursday.
Yeah, Thursday.